Okay, to assist you guys on the quiz 8 problems that have to do with piecewise functions, we're just going to do a bit of a recap of what we know about piecewise functions and work through a couple of examples that are similar to the problems on the quiz that might help you guys get through the quiz a little bit more easily. So this first example, I'm giving you a piecewise function and we're going to try to draw a graph from it. And this was something that a lot of students were struggling with on the quiz. So what we're doing here is essentially 3 different tasks. First, we're going to draw this. Then we're going to draw this. Then we're going to draw this. And once we've drawn all 3 of them, we can figure out exactly where our graphs get cut, so to speak, so that we have the correct pieces in the correct places. So let's just focus on the red part of our piecewise function. This is negative 1/2 x minus 3. And I'm not even going to focus on the domain right now, the x is less than negative 2 part. I'm just going to look at the function itself. So negative 1/2 x minus 3, that's a line. And with a line, it's pretty easy to identify your slope and your y-intercept, and you can draw a line on a graph pretty easily just by looking at what you're given. So if this is a line that starts at the y-intercept of negative 3, and it has a slope of negative 1/2, we go down 1, right 2, down 1, right 2, down 1, right 2, forever and ever in both directions. So this line would look like this, forever in both directions. Now, obviously, that's not what this is going to look like at the end of the day. We have to take our domain into account, but I just wanted to talk about what this line looks like in general. So now let's think about our domain. This line applies only when x is less than negative 2. Well, that would be, this is negative 2 right here. So that's going to be to the left of the black line that I just drew. So x is less than negative 2 is going to be basically from here over. So the line I drew to the right, so I have the line continuing all the way to the right, we have to erase that. And I drew one line like a silly person, so I'm going to have to redraw this. So our line essentially needs to start here. Let's do a better job of that. At that x is less than negative 2 mark. So I'm going to erase everything else. Now, we always have to focus on our endpoints as well in a problem like this. My choices are, I might have an open endpoint here, or I might have a closed endpoint here. And let's talk about the difference. The difference is this symbol, our inequality symbol. If it's a strictly less than, that means that negative 2 is not included in the domain of this part of our function. So we would get an open circle. If it's a less than or equal to inequality, that means that the negative 2 is included in our domain. So like the less than or equal to part means it could be equal to negative 2, so negative 2 is included. So in that case, we would get a filled in circle. But since we have a strictly less than, we're going to get an open circle. Whoops, let's do that in red. We're going to get an open circle right there at that point. So notice, in order to figure out exactly where to put that line, I had to draw the whole line. I had to look at where the y-intercept would be, which was down here, which isn't even part of our domain. But you might have to draw the whole line and then kind of erase to get it into just that domain part. Okay, so now let's focus on the green. For our green part of our piecewise function, we're dealing with a parabola. This is a negative 3x squared plus 5. So your transformations become really important. To draw a parabola, we would start with our parent function, which looks like this. This is a parent function parabola, just a regular old x squared. But then we're going to use transformations to flip it over the x-axis because of the negative in the front. So then it would go down like this instead. 4 down. So we flipped it. Then because there's a 3 in front of the x squared, that's a vertical stretch. So that's going to stretch it up by a factor of 3. So I'm going to zoom in here. Instead of going to the point -1, -1. It's now going to go to the point -1, -3. So we need to stretch it by a factor of 3, which is going to make it 3 times as tall, essentially. So our second point would be here. And then instead of our third point being at 4, our third point needs to be at 12. Uh-oh, I might run off the graph here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 would be like all the way down here. That's really big. So our parabola, because of that stretch, is going to go all the way down like this. It's going to be super tall and super skinny. And then finally, there is a +5 that's going to shift our parabola up 5 units. So transformation's really important here. 1, 2, 3, 4, 5. So we shift it up. And then 1, 2, 3. Here's our second point. And then our third point was at 12 units away. So that was 1, 2, 3, 6, 9, 12. Something like that. I think I'm pretty close here. All right, so now we draw our parabola, which goes on and on forever in both directions. This is the most awful parabola I've ever drawn. But notice I haven't taken my domain into account yet. My domain tells me that this function is only going to exist within the domain where x is in between -2 and 1. And notice it's -2 is less than or equal to x, so -2 is included, whereas x is less than 1 means 1 is not included. So -2 is included, +1 is not included in our domain. So let's figure out where those 2 points are. -2 is right here. Go figure, we're reusing that same line. And +1 is right here. So these are the 2 places where we're going to chop this graph. So I need to erase everything that's green. I'm going to erase that's on the left of this line and then on the right of it as well. But that's going to erase everything because, again, I don't know if that looks good. All right, so now think about your endpoints. -2 is included in our domain, and +1 is not included in our domain. So our parabola part's going to look like this. And let's just pretend that this has like a hump at the top. I didn't do a very good job of that. All right, finally, we have the easiest of the bunch, I hope, the blue part of our function here. This is just -1 if x is greater than or equal to 1. Well, the line -1 is a horizontal line that just goes here forever in both directions. But now we need to take our domain into account. This only applies when x is greater than or equal to 1, which is this line right here. Go figure, the one we just used. So that's where this function's domain starts. And it's or equal to was part of our inequality. So we're going to have a filled in circle because that will be included. So this will go on forever. So here's our piecewise function. Notice this is a problem that requires a lot of steps. You have to draw each of the individual functions, and then you have to figure out where to cut them off so that they have the proper domain. Are there questions about this example so far? Anybody online or anybody in the class have questions? Okay, we're going to answer just a few more questions about this problem. They want us to evaluate, well, I want us to evaluate a few points. I'm giving us x values, we want to find the y values. We have options here. You can either use your graph to find the answers here, or you can use the original function in its kind of algebraic form up above. So you can do either thing, and we're going to do at least a couple of them. We're going to do them both ways. So let's start with f of -3. That means we're plugging -3 in for x, and we want to find the y value. So let's first do it graphically. If I look at -3 on my graph, that's here, my y value at that point is this point, which looks to be about -4/3, but we can also use our graph or use our function to find the point as well. And let me show you how we would do that. Instead of relying visually on the graph, we're going to take -3, and we first have to figure out which piece of the domain -3 fits into. If x is -3, is it greater than 1? No. Is it between -2 and +1? No. If x is -3, then x would be less than -2. So we would need to plug -3 into the red piece, or this domain's section of the piecewise function. So we would put -3 into the red function, which would give us -1/2 times -3 minus 3, which is +3/2 minus 3, or 3/2 minus 6/2, which is -3/2. Okay, so my picture wasn't very good. I thought that looked like maybe -1 1/3. It's actually supposed to be -1 1/2. So sometimes a graph isn't the best option to find a point, especially if it doesn't go through a nice, neat intersection. Give me just 1 second. Yeah, Zach, did you make a hall pass?
Yeah.
Let me approve it, and you're good to go. Just close the door on your way out. Okay. So you would repeat the same process with these other x values we want to plug in, but I want to do some of these graphically more than I want to do them algebraically. So let's look at the next one, f of -2. This type of problem threw a lot of students off. If I find -2 on my graph, that's here. My points that I can see visually are here and here. Many students on the quiz said that there were two answers, -2 and -1, 2, 3, 4, 5, 6, 7. So many students said, oh yeah, this is -2 or -7. That is not right. There is a big difference between an open circle and a closed circle. Open circles mean that those points are not solutions. They are not included. So an open circle kind of just represents a boundary, but it's not an actual point on the graph. Whereas a closed circle, we'll even color in the O there for visual effect. Don't ask, I'm feeling weird today. So a closed circle is a solution. It is included. So when you're looking at these two options here, -2, -2 is not a point on our graph, but -2, -7 is a point on our graph. So the answer here would just be -7. Okay, I saw that mistake on quite a few quizzes. If we were to find f of 0, we would just find our point at the x value of 0. That one's pretty easy. That gets us +5. F of 1, here's another one where we have to be careful. We have two potential y values at x is 1, but based on what we just talked about, an open circle is not a solution, a closed circle is. Our answer would be this one right here, so that would be -1. And then an easy one, f of 2, would just be right here. Nothing tricky about that. That's also -1. Okay, any questions about this whole first example that we just did? Okay, we're going to move on. We're going to do another very similar example, but in this example, we're kind of going in the other direction. So we're starting with a picture, and we want to write the piecewise function. So I've got this f of x here, and I didn't know how to type this on my screen, so we're just going to have to write it in. We're going to have 3 different pieces to our function because we have 3 different pieces to our graph. So I'm going to color code these to make this easier to talk about. We'll make this parabola piece red. And the graph that I pulled doesn't have an arrow here, but you should imagine that arrow goes on forever. We'll make the next one green. This is an open circle, closed circle. And then I'll make the last one blue. open circle. And then this side as well will have an arrow that goes on forever. So for this example, I'm going to start on the left. We usually start from the left and then go right in the order that we list our functions. So we'll start with the red parabola on the left. This parabola, we're going to need to use parent functions and transformations to actually write the function itself. So this is a x squared parent function, but we might need to change some things, add some things, subtract some things to get it into the right shape. So first, let's look for a flip. Is there a flip? No, this is a positive parabola. It faces up. That's good. So we don't need to put a negative out front. Is there a stretch or a condensing? Is it getting taller and skinnier or shorter and fatter? Actually, yeah. Normally, parabolas are supposed to go through the point 1, 1 and 2, 4, like this. But it looks like our parabola has gotten kind of shorter and fatter, so this is a condensing. So we need to figure out what factor this has condensed by. So let's focus on these two here. So normally a parabola goes through the point 2, 4, but this one goes through the point 2, 2. That means we've cut it in half. We've reduced it, we've condensed it by a factor of 2, or think about it as cutting it in half. So we'll put a 1/2 in front to represent our condensed height. So then we also need to look for a shift. Was there a shift left or right? No, so we don't have to worry about anything inside the parentheses here. Was there a shift up or down? No, so we don't have to worry about anything outside here either. So it looks like our parabola is just 1/2 x squared. So that's going to be our first function, 1/2 x squared. And now we need to find our domain of the parabola itself. Well, the domain of this goes from +2 all the way down to -infinity. And notice, this is really important, this is a filled in circle. So positive, oh, I said +2, that's actually 1. I wasn't looking at the scale of my graph. That's +1. So it goes from +1 all the way down to -infinity, and +1 is included because that circle is filled in. So the way we would write that is x is less than or equal to 1. That's our domain of our red parabola here. For the green piece, this is a horizontal line, so those are really easy. That's just like y equals and whatever the y value is. So here that would be y equals 3. But we don't call it y anymore. We call it f of x because we're advanced. So this is just 3. Y equals or f of x equals 3. And then we need to figure out our domain. Well, the domain of the green piece of our function, it goes from 1 to 2. That's it, from 1 to 2. 1 is not included in the domain. 2 is included in the domain. So we write it like this. 1 is less than x is less than or equal to 2. So we're just sandwiching x right in between. I did notice on the quiz, some students are writing their symbols backward when they do something like this. Be careful. If x has to be in between 1 or 2, x has to be bigger than 1, and it has to be smaller than 2. So make sure your symbols are facing the correct directions there. You might have to spend an extra minute or so actually thinking about it and just being really cautious with that. Okay, moving on to our last piece. This is a line. This is our blue piece, sorry. It's a line with a positive slope, and in order to actually figure out the details of this line, I'm going to just pretend like it continues all the way down in this direction because I need to see what its y-intercept would be. This lines usually are represented by mx plus b, where b is our y-intercept, which in this case is 0, and m is our slope, which in this case rise over run would be like 2/2, which simplifies to 1. So this line is represented by this simple, very nice and simple equation, y equals x, after we've figured out our slope, figured out our y-intercept, and simplified everything down. So our equation here is just x. And now it's time to find our domain of the blue line. So I've got some erasing to do. All right, so our blue line starts here with an open circle, and it goes forever to the right. So this would be the point 2, x is 2, but 2 would not be included. Everything to the right of 2 is included all the way up to positive infinity, so we would represent that with just x is greater than 2. Now notice, in a piecewise function, your domains should kind of match. Your first domain should end where your second domain begins. Your second domain begins where your third, or ends where your third domain begins. So they should kind of begin and end in the same places. And another thing to watch out for is if 1 is included in this domain, 1 should not be included in this domain. Right? Only one of them should be included. Whereas if 2 is included in this domain, it should not be included in this domain, right? So only one of those should be included. If they were both included, hypothetically, you might have a function that looks like this. But I just called it a function. It's technically not a function because it doesn't pass the vertical line test, because then you'd have 2 points on the same vertical line and it would no longer be a function. So this whole lesson was about piecewise functions. So these should all be functions. So just watch out for little things like that. Those were mistakes that I saw. There's one more thing I want to address about a problem like this, and that's the range. I'm seeing a ton of range mistakes as well. So let's talk about the range of this function. 2 really, really important things I want to point out. Tons and tons and tons of people were saying the range went from here up. That's not true. There's stuff down here. The range goes lower than that endpoint. So the range of this function actually starts at 0. Notice there's nothing below 0 ever, but it starts at 0 and it goes up. A lot of people were forgetting about these too. These have arrows on the end of them. So they might go up forever or down forever depending on your problem. So I noticed some people were doing problems like this, where this arrow was up above this endpoint. So they just kind of said, oh, okay, our range is from here to here. But it's not, because you have to imagine this arrow keeps going forever and ever, okay? So don't be visually tricked by something like that. An arrow literally means that this thing keeps going. So look for that. So the range on a problem like this goes from 0 all the way up to infinity, and you always start with your smaller number and go up. Some people were writing it like this. That's backwards. Don't do that. You always start small, then go up. And make sure this would be included, so it would get a bracket and not a parenthesis. Little details like that. So just watch for that sort of thing. Okay, so that concludes the review I wanted to do on piecewise functions, unless anybody has questions about it. Any questions about the examples we just did? How you doing? Good? No questions? Online students, you feeling okay about this material? Okay, I hope that helped. In addition, it just came to my attention earlier today in class that you guys might not know what an inverse is, and I was afraid of that. So I typed this up just in case you didn't know. And this is something you'll probably want in your notebooks. This is a definition. We've talked about composite functions. Well, there's a definition of composite functions that can help us in certain types of problems, especially finding the range. I figured since you guys have been working with range for so long, you would have already known this, but inverses are a way we can algebraically find the range of a function instead of drawing it. And composite functions are the method we use to identify an inverse. So one important definition of the inverse property is if you have 2 functions, let's just call them f and g. If you can plug g into f and it spits out x, or if you can plug f into g and it spits out x, those 2 functions are called inverses of each other. Now let me explain what that means. Here's an example of 2 functions that are inverses of each other. Another way to think of inverses is kind of like they're opposites or that they undo each other. If I were to take f of g of x in this example, I would start with f, which was x minus 4, but instead of plugging in x, I would plug in g, which is x plus 4. So this would give me x plus 4 minus 4, and essentially what's happening is the x plus 4 and the x minus 4 kind of undo each other because they're sort of opposites. Now you could do something similar with like f of x equals 2x and g of x equals 1 half x. These would be inverses because if you plug one of the functions into the other, the 1 half and the 2 are going to kind of multiply together to undo each other because they're inverses of each other. They're multiplicative inverses. So these are very, very simple examples to show you what an inverse is and what it means to kind of undo another function. But now I want to show you how to find an inverse if you haven't done this yet this semester. So let's do a simple example. If I wanted to find the inverse of 3x plus 2, thank you for letting Zach back in. If I want to find the inverse of a simple function like 3x minus 2, here's the process. First things first, we don't leave this as an f of x, we're going to write it as a y. That's just because it's easier to do algebra with y's than it is to do algebra with all of that nasty notation with the f of x and the parentheses and whatnot. So let's rewrite this as y equals 3x plus 2. Step 1, switch x's with y's. This is a weird Frankenstein move. This is the only time in algebra you'll ever do anything like this. We can never, ever just normally do this. But we're going to make every y an x, and we're going to make every x a y. So this becomes x equals 3y minus 2. Then solve for y. So we just need to get y by itself on one side. We're going to add 2 to both sides. So we get 3y equals x plus 2. Divide both sides by 3. You end up with y equals x plus 2 over 3. And since we're advanced algebra students now, we don't write it as y. We're going to change y back to whatever we're calling our inverse function. So normally you'd call it g of x. You can call it whatever you want, just give it a name. So we're going to erase the y and make it a g of x. And that's how you find an inverse. So there's a question on your homework where they don't use the word inverse, but what they say is find a function g so that f of g equals x. That's what an inverse is. They're essentially saying find the inverse of f. So what we do is that 3-step process. We write y equals 7x plus 5 over x plus 8, and we switch our x and y. So every x becomes a y, every y becomes an x. We've got a few that we have to do here. So we get y, I'm already making mistakes. We get x equals 7y plus 5 over y plus 8. And now we need to solve for y. So that means get y by itself on one side. And that's going to be a little tricky because we have multiple y's. We've got one here and one here. And some of our y's are in the denominator of a fraction. So the first thing I'm going to do is multiply both sides by y plus 8. That's just going to get rid of this denominator. So I end up with xy plus 8x equals 7y plus 5. And to get y by itself on one side, we need to get all of the y's on one side. So I need my xy and my 7y to be on the same side of the equation. I need everything else to be on the other side of the equation. So I'm going to move the 7y over to the left, and I'm going to move the 8x over to the right. So that'll give me xy minus 7y equals 5 minus 8x. Now that we have on the left-hand side of our equation, now that we have only terms that contain a y, I can factor out a y. So I'm going to pull a y out front, which leaves me with x minus 7 in parentheses. And then finally, I get this y completely alone by dividing both sides by x minus 7. So you get y equals 5 minus 8x over x minus 7. That is our inverse. Now, keep in mind, step 3, you'll change y back to function notation. And the letters you use for your function notation are going to depend on the problem. I think here they tell us to find a function g, so we're going to call our inverse, we're going to call that g of x. So we'll just cross that off and we'll just write it as g of x instead. So this is our inverse. This is our g of x. 5 minus 8x over x minus 7, and that's what you plug in right here.